All right, so today we'll continue induction as we will for the next couple of lectures. But I think it's really important to get an example of induction that isn't just a summation, right? Which are the examples that we looked at last time. So let me start with, so I'll just call this 4b because we're going to continue for a couple more lectures. So let me state the following theorem. So for all natural numbers n, 3 divides n cubed minus n. Okay, and here's where I would ask if this theorem looks familiar to you, which hopefully it does, because what does it mean to say that 3 divides n cubed minus n? Another way to say this is to say that n cubed is congruent to n mod 3. So we've proven this once already. Back here? Here? Where do we do this? You remember, right? Maybe it was back here. Oh my gosh, I'm losing it. Yeah, man, someone who had prepared their lectures better would know where to look. Okay, well, you remember proving this, right? For all n and n cubed is congruent to n mod 3, and what we did is we broke into cases, right? Which is a good way to prove it. But now we can also prove this by induction because it's a statement about all integers n. So let's prove this by induction. So we prove by induction. Always tell your reader what you're doing. Okay, so first we do a base case, and here it's for all natural numbers n, which means that the base case is 0, right? So for the case n equals 0, n cubed minus n equals 0 cubed minus 0, which is 0, which is 3 times 0. Right? So therefore n cubed minus n is equal to 3 times something. So by definition of divides, or of divisibility, 3 divides n cubed minus n. Maybe I should say 3 divides 0 cubed minus 0. It holds for this particular n, right? So that's good. We always do the base case first, and now we have the inductive step. And the inductive step allows you to assume that it's true for the kth natural number, and then you need to use that to prove that's true for the k plus first natural number. Right? So in the inductive step, you prove that the kth domino knocks over the k plus first domino. So assume for some natural number k that 3 divides k cubed minus k. And this thing is called the inductive hypothesis. It's where you assume the kth case in the inductive step. Right, and since we're doing a proof by induction, what we need to prove, so we must show that 3 divides k plus 1 cubed minus k plus 1. Right, that's the k plus 1th, the k plus first case. So now observe that, well, the only thing to do is to try to manipulate this, right? So k plus 1 cubed minus k plus 1 is k cubed plus 3k squared plus 3k plus 1 minus k plus 1. Right, that's just some algebra, which is equal to k cubed plus 3k squared plus 2k. Okay, so I need to show that 3 divides this, right? But the thing that I know about is I know that 3 divides k squared minus k. Sorry, k cubed minus k. So I need to somehow understand this in terms of k cubed minus k. But this is the same thing as k cubed minus k plus 3k squared plus 3k. Right? That's just it's like I unsimplified it. Now, by the inductive hypothesis, since 3 divides k cubed minus k, there exists an integer m such that k cubed minus k equals 3 times m. That's what it means to say that 3 divides k cubed minus k. Right? Hence, actually, this thing that I'm interested in equals 3m plus 3k squared plus k. Let's do one step at a time. It's this, right? All I've done is I've just replaced this with this because they're equal. Right? All the yellow things are currently equal. And this is equal to 3 times m plus k squared plus k. So by the closure of the integers, all of these things are integers. So by closure of z, m plus k squared plus k is in the integers, right? Because we assume that, or here we know that m is an integer. We know that k is a natural number, which is an integer. So k squared is an integer. So hence 3 divides k plus 1 cubed minus k plus 1, because I've written k plus 1 cubed minus k plus 1 as 3 times an integer. So that completes the inductive step, which means, so in the inductive step, I proved that the kth case implies the k plus first case. And so therefore, by induction, I've proven the theorem that I want. Hence, by induction, or by the principle of mathematical induction, 3 divides n cubed minus n for all natural numbers n. Okay, so this was, I guess, your third example of an induction proof. But this one wasn't just some kind of summation, right? I can probably actually move this up a little bit to try to get this better printing on one single slide. So proof by induction is a much more flexible technique than just proving things about summations. And again, let me just point out, since I said this last time, induction is a very powerful tool because the base case is often very easy. And the inductive step gives you something very concrete to prove, right? Because you get to start with something, you get to assume the kth case, and then you have a very clear target to aim at. So doing an induction proof is like oftentimes like almost rather formulaic, although maybe you need to think a little bit in the inductive step. But there are some subtleties involved. Okay, so let me give you the classic example of the subtlety of induction. And I really want you at some point, when I tell you to do this, you should really pause this video and try to figure out what's happening. Okay, because if you just watch and I tell you the answer, you're not gonna learn very much from me telling you the answer. Okay, so here's I'm gonna call this a non-theorem. So subtlety. Right, because again, induction seems very formulaic, so you might just fall into a groove of just doing the thing that you know you need to do for induction. But if you're not careful, you can run into some problems. So let me state the non-theorem. For all natural numbers n greater than or equal to 1, for any collection of n horses, all of the horses are the same color. So I'm going to prove that in any collection of 1 horse, they're all the same color. In any collection of 2 horses, they're both the same color. In any collection of 10 horses, all 10 horses are the same color. In any collection of 15 horses, all horses have the same color. So that means that as a corollary, all horses are the same color, right? Because there are only finitely many horses on Earth that have ever lived even. Okay, so let me give you a proof. But since this is a non-theorem, I'll call this a false proof. So we prove this by induction. Even in our false proofs, we should try to write them well. Right, so for the base case, when n equals 1, I need to show that any collection of one horse, in any collection of one horse, all the horses have the same color. But of course, that's obvious, right? If you have a single horse, it's the same color as itself. And so it's the same color as every horse in that collection, right? So I said that you shouldn't use the word is obvious in math, but since this is a non-proof, it's not about mathematical things really. It's about horses. So it's obvious that in any collection of one horse, all horses have the same color, because the only horses you need to check are just the single horse, which has the same color as itself. Right? Even if that color is multicolored, or right, brown and white or something, then you'll say that horse is, all horses are brown and white colored. Okay, now let's do the inductive step, which is where the interesting thing happens. Okay, so assume that the statement is true for some k. For some natural number k, right? So this is my inductive hypothesis. I get to assume the result for any collection of k horses. Now suppose I have a collection of k plus 1 horses. I need to show that they're all the same color. Okay, but let me draw a picture, right? So my horses, I'm like a physicist, my horses are going to be just massless circles, right? So here's k plus 1 horses, right? So let's put it even a dot 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 here. So 2, 3. Actually, I didn't need to draw this many, but k plus 1. So here I have k plus 1 horses. Okay, but by the induction hypothesis, the statement is true for k, which means that any collection of k horses, all of them have the same color. So here is a collection of k horses. By the induction hypothesis, all of these have the same color, right? Because I get to assume the statement is true for k. So by the induction hypothesis, I guess I'll write it in blue. The horses, or the collection of horses, one through k, all have the same color. I'm allowed to assume the induction hypothesis and induction argument, so that's fine. And then the trick here is, if I circle these k horses, these also must have the same color, because that's a collection of k horses, right? Also by the induction hypothesis, the horses 2 through k plus 1, so 2 through k plus 1, all have the same color. That's by the induction hypothesis. But if you look at this picture, right, that means that like 1 and 2 have the same color, but also 2 and k plus 1 have the same color, which means that actually all of these need to be the same color, right? If 1 through k are all brown, they're all the same color, and 2 through k plus 1 are all the same color, that color must be brown, which means that all the horses are brown, right? So therefore, by induction, or right, so let's just say, therefore, all k+1 horses here have the same color. Just look at the picture. If everything in the red box has the same color and everything in the blue box has the same color, actually all these horses must have the same color. So by induction, all horses have the same color, or all collections of n. All collections of n horses are, let's say, monochromatic. That's a fancy way to say they have the same color. Okay. So this is the kind of thing that works much better if we were in a live lecture. This thing, there must be some problem here, right? By the way, just because you prove something crazy doesn't mean that the crazy thing is false. So actually, if you're kind of convinced by this argument, then I think if you're like a mathematician, which you guys are, some percentage of the way to being mathematicians, this argument is actually pretty convincing. And then you might even start believing that maybe all horses are the same color. And there are some really crazy theorems out there that end up being true in our mathematical system. So there are lots of theorems that are like called paradoxes because they are true but unexpected. So let me just give you a list. So crazy things that are true. Right, so like the Banach-Tarski paradox, you should look these things up. You don't have to, but you could. I mean, from calculus, maybe you learned about Gabriel's horn, which is like the way that it's sometimes stated is there exists a surface that you could fill with a finite amount of paint, but you could never paint the entire surface. It has finite volume, but infinite surface area. Banach-Tarski's paradox, I think, is actually even more surprising. Like the existence of space-filling curves, I think, is really surprising. That you can take a curve and actually get like a non-zero area. There's a lot of work in logic by Kurt Gödel. So Gödel's incompleteness theorem. There's all kinds of really crazy results in mathematics that are true. So just because you come across something crazy doesn't mean that it's false. So as a mathematician, I'm actually kind of convinced by this argument. Kind of. However, it's clear that there's something wrong with this, right? Because it's false. It's obviously false because you can come up with a counterexample. So the question is, where is the false part of this proof? Which part of this proof was not kosher? Okay, and I really want you to pause the video right now and try to figure it out. Okay, because if I just tell you the answer, you haven't learned anything. Okay, so let me tell you the answer now. You're such a good student that you already paused the video and figured it out yourself. So let me tell you the answer. So remember, the reason that an induction proof works is because you prove a base case and then you prove the inductive step, which means you prove that the kth domino always knocks over the k plus first domino, and then you knock over the first domino. Right, so the base case here is definitely okay. Hopefully you agree. Which means that the problem must be in the inductive step. And the problem with this inductive step is that the inductive step doesn't work when k equals 1. Because the picture is misleading when k equals 1. Right, so this inductive step needs to work for every single k. Because the first domino needs to knock over the second domino needs to knock over the third domino needs to knock over the fourth domino. Right, so in this inductive step, it does work as long as k is 2 or bigger. Because if k is 2 or bigger, this picture is accurate even for 3, right? It's like these are the same color, these are the same color, there's an overlap, therefore all the horses in this group are the same color. So if it were, I mean, this inductive step works as long as k is not 1. But if k is 1, the inductive step, what I've drawn, actually looks like this. The base case is true. Every collection of horses containing one horse, all the horses have the same color. But in this inductive step, when I took 2 horses for that particular inductive step, all the first k all have the same color. The last k all have the same color. But that doesn't imply that all the horses have the same color, because in this case, there's no overlap. So in this proof, basically, we can knock over the first domino, but the first domino doesn't knock anything else down. And if the second domino fell over, it would knock over the third domino. And if the third domino fell over, it would knock over the fourth domino. So this inductive step basically is almost entirely correct, right? Except that it misses the very specific case of k equals 1. And if you try to start the base case at k at 2, the base case wouldn't be true. So you can't knock over that second domino. Okay, so what this says is that even though induction seems very like algorithmic, you actually genuinely need to be careful. Otherwise, you might accidentally prove things that are very false. Or more likely, you'll have a subtle error in your proof of a true statement, but the proof will be wrong because you haven't accounted for something if you're making some assumptions that you don't know that you're making when you prove the inductive step. Okay, but basically this example is the most famous example in terms of subtleties in proof by induction. So everybody, as soon as they learn induction, should see this example and figure out what went wrong. So I hope you did that. I trust that many of you did. Okay. So one thing that we haven't really done yet is look at an example where the base case was not 1 or 0. And I mentioned last time, I mean, the technique of mathematical induction started at 0, but then I mentioned that actually you could start your induction sort of anywhere. And your book makes a distinction between starting at 0 or 1 and starting somewhere else. So your book says that, like, if you're starting at 5, they would call that the extended principle of mathematical induction, because the statement of this technique here, I specifically said 0, right? But any normal mathematician would just call it the principle of mathematical induction, so I'm not going to call it something different. But I do want to give you an example where the base case isn't just 0 or 1. So let me give you a very nice, interesting thing. I'm going to call this the McNugget problem. Okay, McNugget for the chicken nuggets at McDonald's, which some people consider delicious. I like them personally, although I've never been to a McDonald's in Seattle because is there even a McDonald's anywhere close to here? Okay, so suppose that at McDonald's, there are several sizes of McNuggets that you can order. Okay, so whenever I first wrote these notes, I think I actually looked up the sizes of the McDonald's McNuggets. But you can actually order many different kinds of McNuggets. But so let's suppose that you go to some McDonald's. You can either order 4 McNuggets and a Happy Meal. I'm using all kinds of trademarked things in this lecture. Or you can order 5 McNuggets as the regular order, right? And let's suppose there's no 10 pieces or 20 pieces, just to make this thing as simple as possible. Okay, well, you can obviously get 4 McNuggets. You could also get 8 McNuggets by getting 2 Happy Meals. You can get 9 McNuggets by getting a Happy Meal in a regular order. But there's no way that you can possibly order 6 McNuggets. right? Just 6. I guess you could order 8 and then throw 2 of them away, but that would be terrible, right? So you can obviously order 4 or 5 or 8 or 9 or 10 McNuggets, but you can't order 6, it seems like. So a question is, what are the possibilities? What are all the possibilities for the number of McNuggets that you can order? You obviously can't order any number of McNuggets, but you can order a lot of different orders of McNuggets. How many can you order? Okay, this is I mean, it's called the McNugget problem because, I mean, it has a name. That means it's a common thing to think about in mathematics. How could you go about, right? Imagine I gave you this question. How would you go about answering this? And the thing to do, basically the only thing to do is to, at this point, is to try to generate some data to see if we can order certain numbers of McNuggets. Then once we have the data, we can look for some understanding of what's happening. And once we understand what's happening, we can try to prove it. Okay, so let's consider different values of numbers of McNuggets that I want, right? So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. And again, here, if we had a live lecture, I would ask you to figure out how to order these amounts of McNuggets if you can. So maybe you can pause the video and do that. I'll just do it for you. So we obviously can't order 1, 2, or 3 McNuggets. Oh, maybe, okay. We can order 4, or we can order 5 just by ordering a single 4 or a single 5. That's what I mean by that. You can't order 6 or 7. There's no way to do that. But you can order 8 by ordering 4 plus 4. You can order 9 by ordering 4 plus 5. You can order 10 by ordering 5 plus 5. Because I want you to continue this table. Now, can you order 11? So if you start with 4, then you'd have to get 7 more, which you can't do. If you started with 5, you'd have to get 6 more, which you also cannot do, right? Because you can't do 6 or 7 here. So no matter how you start, you can't get 11. Right? But you can get 12. Right? How do you get 12? You just ordered 3 4s. You can get 13, 4 plus 4 plus 5. You can get 14, 4 plus 5 plus 5. And you can get 15, 5 plus 5 plus 5. Then you can get 16 as 4 plus 4 plus 4 plus 4. 17 as 4 plus 4 plus 4 plus 5. 18 as 4 plus 4 plus 5 plus 5. And then it seems like you can always continue this forever, right? Because if you ever have a 4, you can, in your sum, you can get the next highest number by replacing that with a 5. So I can get 19 just by replacing by a 5. I can get 20 by replacing that one with a 5. And then once I get to 20, so what happened when I maxed out all my 5s? If I maxed out all my 5s, then I can take 15 of them in 3 groups of 5 and replace them with 4 groups of 4. To get from 15 to 16, I switched from 3 5s to 4 4s. So it looks like up until 11, you maybe can or can't. But from 12 onward, it's always possible to order at least 12. And then the small cases we could do by hand. So it looks like you can order 4, 5, 8, 9, 10, and then any number bigger than or equal to 12. And the thing about this is that this has the feeling of an inductive argument. Because if you know that you can get 16, then you can use that information to get 17, as long as you know something about the 4s and the 5s that you've used. So because of this, we can prove this by induction. And I think it would be hard to prove this rigorously any other way, right? You could probably convince your friends that you could do this by showing them this table and be like, oh, well, you always replace a 4 with a 5, unless you don't have any 4s, in which case you just replace 5 3s with 4 4s, and then you're done. But to make that rigorous, right, to say like, you can always do this, you should really do this by induction. And this is a good example of an induction that starts not at 0 or 1, but this induction actually starts at 12, very naturally. Okay, so let's call this the McNugget theorem. So for all natural numbers greater than or equal to 12, it is possible to order n McNuggets, right, in batches of 4 or 5. That was our setup for the McNugget problem. Okay, so the base case here, here's a base case that doesn't start at 0 or 1. So your book wants to call this extended principle of mathematical induction, but we'll just call it induction. So when n equals 12, we can order 12 McNuggets by ordering 3 4-piece McNuggets. Right, 3 times 4 is 12. Here's the inductive step. Okay, so assume for some k greater than or equal to 12 that it is possible to order k McNuggets. I want to show that you can actually order k plus 1 McNuggets. How do you do this? Well, right now we don't have any information about the k. But we saw that there are sort of two cases, right? If you ever have a 4, it's easy to get k plus 1. If you don't have a 4, then you have enough 5s to replace 15 of them with 16. So really, we should say there are two cases. Yeah, so there are two cases. Case 1, if we ordered at least one 4-piece to get k, and then case 2 will be if we didn't use any 4 pieces. Those are the two possibilities. We know that we're assuming that it's possible to order k, but we either used a 4-piece or we didn't. So if we order at least one 4-piece to order k, replace the 4-piece with a 5-piece, to order k plus 1. Okay, so if we did not order, if we did not order at least one 4-piece to order k, well, that means that we used only 5 pieces. Right, but now, since k is bigger than or equal to 12, it must be that we ordered at least 3 5 pieces, because 2 5 pieces isn't bigger than 12. So since k is bigger than or equal to 12, which is important, we ordered at least 3 5 pieces. Perhaps exactly 3 5 pieces. So replace 3 5 pieces, which we have ordered at least that many, with 4 4 pieces to order k plus 1. And then, right, so we've shown that no matter what the case is, you can always order k plus 1 McNuggets if you can order k. So by induction, we can order any n greater than or equal to 12 McNuggets. So there's two nice things I like about this. Actually, there's at least three nice things I like about this theorem. Okay, so one of them is that it's a very natural induction where it doesn't start at 0 or 1. Because almost all the examples we see at first start at 0 or 1. It's nice to know that induction is flexible enough to start anywhere in some sort of natural problem. The second thing I like about this is that this proof is like very clean and very convincing because it uses the power of induction. Again, when I explained it to you on the previous slide, it seemed a little bit hand wavy, right? It seemed like, well, did he prove it really? But once I've proven by induction, it's like such a powerful tool that it provides like a really clean proof, and now it's extremely convincing. Okay, and then the third thing I like about this problem is that it requires some experimentation to do, right? You need to figure something out in order to prove this, which is, again, another one of the skills that I want to cultivate in this class, right? Even from the very first homework assignment, where I asked you to prove something about triplet primes, and I asked you to come up with some conjectures, I was trying to get us out of this calculus linear algebra mindset where you sort of always know how to do the problem that's in front of you. Sometimes you just gotta do some experimentation, figure out what's happening, and then clearly explain what you figured out in a proof. That's basically what mathematics is. Okay, so hopefully you found today's lecture kind of interesting. I think this was an interesting lecture, but I'm a little bit biased, obviously. So first we proved a result that we proved by cases. So this provided actually a second proof of a result we already knew. Then we saw this horse subtlety, which, maybe you can go talk to your CS friends who learned induction in their CS class or whatever, and then try to prove to them that all horses are the same color. And then this McNugget problem is like a very nice application of induction, I think. All right, so I'll leave it there for today. Next 2 or 3 lectures, we'll continue doing induction, and I think maybe just 2. And there are, of course, induction problems on your problem set, so you should get lots of practice doing these kinds of proofs.